Hello and welcome to a new video. This is for pre-calculus math UC, and we're doing lesson 25, which is about the graphs of tangent and cotangent. So this is going to be our final set of trig functions we're graphing, because we've already done sine and cosine and secant and cosecant. So now we're ready for the last pair, tangent and cotangent. So the first thing to do is to see what do these even look like. So they are going to look similar to each other, but these both actually look quite a bit different from cosine, sine, secant, and cosecant. And that's because of the way of what tangent means, or the connection between tangent and these other trig functions, is that tangent is actually going to come from taking the values of sine over the values of cosine, if you remember that trig identity from a ways back. So I'm going to graph in Desmos and bring it over here. This is the graph of y equals tangent x. So to me, the thing that this looks most like is actually, they kind of look like cubic functions. So if you don't remember what cubic functions look like or haven't seen a cubic function, y equals x cubed looks like this green graph here. So it definitely doesn't look exactly like it, but that's what it reminds me of personally, as something that it's kind of close to. If we're trying to dive into what's going on here, basically we have repeated values happening, and we have asymptotes, kind of like with secant and cosecant. That's coming from the fact that if we're doing sine divided by cosine, any place that cosine would be 0 would put a 0 on bottom of our fraction, and that's a problem. That gives us an asymptote. So here for just like regular y equals tangent x, our asymptotes are at pi over 2, and if we're like focused on the middle here, and then negative pi over 2. And so what that means is that the period of our tangent graph is actually different than what it is for other trig functions. Cotangent and tangent both have a period of pi, because the period of a trig function is how long does it take to have like one unique part of your graph. So for sine and cosine, that meant that we had to go up and then down to have all of our unique values accounted for. Same with secant and cosecant, we had to have like an up part and a down part. But here we're just repeating the same swoosh over and over again. And so it actually only takes pi for us to have all of the unique values. So it has a shorter period, it repeats more often, which is kind of interesting. As we think about what can happen with tangent, the same kind of things can happen. Like we can shift tangent up by adding something. So kind of focus on this point right here where the word that makes sense to me to use is like how it kind of pivots around, or like that's like its starting point where you would start it and then make it go up and down. So that shifted that point up and all of the other values up, because I did a +1. If I did a -1 instead, it would make everything shift down. If we put a shift inside of tangent, and we typically, when we do that, use some radian values, like we could shift over pi over 4. So see how I didn't move my asymptotes, and so you can see how this is shifted over a little bit to the left, or we could do the same thing but with a minus, and that would shift it to the right. We can affect the period of tangent by putting a number in front. So like if I put a 2 in front, it actually squishes it in by a half because it's inside. So that's kind of cool. We could also, make it be wider by putting in a number like 1/2. I don't know why I didn't do this with the other functions, like just mess around in Desmos. It's one of my favorite things about Desmos is that it's so easy to change the graph and to see what's happening to your graph as you type it in. So we can put a number in front of tangent, and what that does is it stretches our graph or shrinks it vertically, and so you can see how it makes it like go up faster, right? You can kind of see the difference there. Or if we put a 1/2, it would actually make it like go up slower. Those are, in my opinion, a little bit hard to show whenever we're graphing. Like we're kind of at the point once we get to tangent and cotangent where as we're graphing it, we have to kind of decide between like how picky are we going to be, how much of a perfectionist are we going to be with trying to make this look exactly right. And so to me as a teacher, what's important is that you've got the middle point that it's pivoting around, that's in the right spot, that you've got your asymptotes in the right spot. And to me, the how quick it's going up or down just doesn't seem as important to me. But definitely check with your teacher or whoever is checking your work to see how they feel about that. If you're doing this on your TI calculator, of course, you can graph y equals tangent x. And in Desmos or on your TI calculator, it can be helpful to change a couple things on the window here to help us. So for the TI calculator, you would press the window button, and it has actually these same settings that I'm showing on Desmos. A standard window will have X. It'll say like X min -10, X max 10. Now, if you've zoom trigged or done other things in the course of graphing for these lessons, then it might be something different, and that's fine. Zoom trig actually is a really helpful thing you can do on your TI calculator, that it'll change this to, it should say like -6.28, which is -2 pi, to +2 pi. And I could actually make that change in Desmos by typing that in. But the even better part of it is changing it's a step on Desmos, or it's the scale on your TI calculator. It's abbreviated SCL, because why put vowels, right? If we change that to something like pi/4 or pi/2, like depending on what you want to do, then it's going to actually show us radian values here. On your TI calculator, it won't have those written. It'll just, how long your tick marks are apart is whatever you put in there. So that can be really, really helpful as you're graphing to be able to see where things are. The other thing that can be helpful is on Desmos at least, is to graph other lines around this. So like how I actually like graphed what I thought the asymptotes were, and so I can see, okay, yes, that's where the asymptotes are. It's another thing that can be helpful. Okay, so I'm gonna graph this on my graph. So we need some asymptotes at -pi/2 and +pi/2, which I like to make myself some dashed lines. Dashed lines typically with something like this would be like, these are things I'm using to help me graph. It's not actually part of the graph. It starts in the middle, goes up to the right, and down to the left. So something like this. And then we could, if we wanted to like fill in our graph, we could do another one here at 3pi/2. Drawing graphs on the computer is one of the best things ever not. It's a little tricky. Okay. Zoop. Zoop. Aren't these like some really beautiful graphs here? Hopefully you get the idea, because I showed you what the actual graph looks like. And I could do much better if I was drawing this on paper than on the computer, but yeah. Okay, let's talk about cotangent. So for cotangent, it is the reciprocal of tangent. So it should look kind of like tangent, or we would think that, right? It's also cosine over sine, so that's how we could get our values. As I type it into my calculator, on the TI calculator, make sure that you don't do second tangent, which is tangent to -1, and that's inverse tangent. That's not what we want. We want 1 divided by tangent. Oh. This going well. So you want to do 1 and then the divided by button and tangent. This is cotangent. And for Desmos, there is actually a cotangent button, which is even better. You go to the functions and you can just put in cotangent and take out the, the iffiness of, oh, what is it? 1 divided by? So we can tell, because I left the asymptotes up, that our asymptotes are moved over, and also helps us tell that our graph is moved over. So this would be, there would be an asymptote at 0, and then there's one at pi. for instance, and then our pivoting point is here in the middle at pi over 2. Now notice this goes down to the right and up to the left, but really that's the main difference. We've got a shift over that's going to affect where our asymptotes are, and we've got it actually going opposite directions, to up and to the left, down to the right. So let's graph this. Still have a period of pi. These asymptotes are pi apart. The graph repeats every pi. So it does have that in common with tangent. So we're going to draw an asymptote at 0, one at pi. We do one at 2 pi. It all depends on how many of these you want to fill in here. Typically in classes in general that are asking you to do things like this, they will either say graph a period of it or graph 2 periods of it, and that would tell you how much you need to graph. Or it could say make a graph of this from 0 to 2 pi, so then you'd go, okay, I have to make all of the things from 0 to 2 pi. This looks maybe slightly better than the last one, I don't know. But if it doesn't technically specify how many it wants you to graph, then you got to graph at least one, right? But then from there, it's kind of like a, who knows? So I just made a couple of examples here because this lesson actually just has like 3 problems on each page, A, B, C, D, and they aren't even all tangent and cotangent. It also goes back and has you work on graphing secant, cosecant, sine, and cosine. So I don't think that there's a lot, there's not really a lot new here. Like, we basically are still going to use our calculator to help us probably graph it. Still make a table of values if that's helpful to you. We're still describing things like the shift, the period, and the translation, telling where the asymptotes are. They do give you graphs in this lesson in the workbook, which is nice, but also kind of weird because I tried to model this graph that I put on the notes here off of it, and you'll notice that it gives us from basically from 0 to 2 pi with a little extra room on either side. So that's different, I feel like, than what you've probably been graphing before this. It might feel a little weird to graph from 0 to 2 pi instead of to graph on either side. But I have complete confidence in you. You've got this. Let's go and graph tangent of x plus pi over 4 minus 1. So the same things are happening here that happened with sine or cosine or secant or cosecant, because if it's a function, then it's affected in the same way. This plus pi over 4 inside is part of the super-secret opposite society, and so this is a shift to the left of pi over 4. So where normally tangent starts at 0 and then pivots, we'd actually have to shift it over, and it would be at pi over 4. And instead of our asymptotes being at pi over 2 and negative pi over 2, it would shift over one little tick mark here. So here would be one of my asymptotes. And so it should have been at pi over 2, and then it should have been at 3 pi over 2, but we're going to shift it over here. Ooh. And then our pivoting point would be in the middle. But wait, we are also shifting down. I actually legit kind of forgot this. We also are shifting down 1, which on this graph actually does something interesting. If we shift this down 1 and then draw it, when I first graphed this in class, I was like, wait, this looks the exact same. And it's because of the combination of where we shifted it. So this goes, because it actually ends up going through 0, 0. That's beautiful. So it goes up to the right and down to the left. So it looks something like this. I do want to show you on Desmos. The period of the graph is pi because the thing that affects the period is a number that's in front of x, and we don't have one, so it's just a normal pi. This is x plus pi over 4. Minus 1. Okay, So if you are trying to graph this and you're using your TI calculator, using the table of values can be super helpful. If you're trying to graph this and you're on Desmos, we don't have a table of values, but we can click here and like drag. It will show us like points, like it shows us where this intersection is. But what would be really nice is if we actually knew for sure where the pivoting point is. So because it's shifted down one, if I put in y equals -1 here, then I can actually see where that pivoting point is. I can click or touch on my phone and see what that is. I can also mess around with, you know, where would the asymptotes be if I want to. So it looks like pi over 4 would be one of them. But then I can graph and say, oh yeah, that is pi over 4. And I gave a slider for y. I don't know why it wouldn't have given a slider for this one also, because that would be maybe because I did pi on it and it had to calculate. So I was going to say it'd be kind of nice actually if we could use a slider to slide the line back and forth if we didn't get it right the first time. So -3 pi over 4. So we can use other lines, vertical lines are x equals, horizontal lines are y equals, to kind of help us see what are some points that I can graph on Desmos. So that can be helpful. The asymptotes, so I like the idea of just listing a couple of the asymptotes, like x equals pi over 4, 5 pi over 4, and then that's a pattern that continues on after that and actually goes before it as well. But that's where our asymptotes would be. So let's graph example 2 here. So this one's cotangent. So if we're typing this into our TI calculator, we'd have y equals, to do 1/2 is just 1 divided by 2. You can use alpha y equals to make it look like a fraction if you want, or you can actually just put 0.5 and maybe save yourself some trouble. Cotangent is 1 divided by tangent, but like we could just go ahead and put 0.5 divided by tangent instead of having a 1 there. And then you'd close your parentheses and put the +1 outside of parentheses. So something like that should get the job done here. This +1 is a shift up. There's nothing in front of x, so the period, I don't think I actually wrote it down on example 1. The period is pi. This 1/2 is making it so our graph's going to go up and down a little bit slower. Most of the graph still looks really similar. It's still going up and down pretty fast towards our asymptotes. So again, I find it hard to really like communicate the 1/2 part of this, but I mean, you can. It's something that is technically doable. So cotangent normally has asymptotes at 0 and pi, and we're not shifting left or right, so that's going to be the case here, 0 and pi. It goes down to the right and up to the left. Normally at pi over 2 here, pi over 2 comma 0, but it's shifted up 1, so I should put it here. And if I'm trying to do this 1/2 situation, like it needs to like kind of be flatter, close to the middle. Ugh, I just love graphing on the computer. It's so great. So then my next one would be here. Sorry for complaining. I shouldn't complain. It's amazing that I can graph on my computer. Back when I was a kid, I don't know if we could graph on a computer like this. So there we go. That's what cotangent looks like. We've got asymptotes at 0, pi, 2 pi, and so on. A shift up, no shift left or right. The period is pi. So that's the idea. Thanks so much for watching. Hope you enjoyed the video. Please give me a thumbs up. It really helps out whenever you press that like button for YouTube, and subscribe if you haven't already. And I'll see you in the next video. Bye.